Hello, everyone. This is going to be talking about Chapter 5, which is Engineering Science. And we're going to go over specifically looking at different forms of energy and energy transfer models. And so within this review, we're going to be looking at specifically the law of conservation of energy. And then we're going to learn about objects' momentum and then how a change in momentum is going to generate an impulse. So through this cumulative guide in electrical engineering project, we're going to be trying to just combat a lot of the difficulty faced within the engineering curriculum. And so let's get started. So what is energy? So energy of a mass represents the ability for that mass to do work. And so you can think of how much energy we have. And so for humans, if we have a lot of energy, we can do a lot of work. We are able to move around and get things done. And so if we have a lot of energy, we can get a lot done. But if we don't have much energy, we can't do much. And so this can also be applied to objects. So what we're going to see is maybe an object is, say we have a ball, and that's at a very high elevation. So it has a lot of potential energy right now. It's at like on top of a hill or something. So it's at a very high height. So it has a lot of potential energy. So we're going to look at different types of forms of energy, but that's just one form because this ball can fall down and do work. So it can fall down the hill and start to roll. And so we're going to see that ball has a lot of potential energy stored in it at the top because it's able to fall down and start to move and perform work. So work deals with changing a mass's energy. And so we're going to see work is performed by taking the dot product. So here this represents the dot product of the force vector acting through displacement vector. And so what you're going to notice is work is measured in units of joules, and our force is measured in units of newtons, and our displacement vector is in units of meters. And so work is positive when you're forced, so you're applying a force, so you're either pushing or it can be pulling. So work is positive when a force acts in the direction of motion. So we're going to see that our force is in the same direction as our displacement vector. So if I'm pushing in the direction of movement, then that is going to be positive work. But if the force opposes the direction of motion, so say that we have a box that's moving, but the force is opposing it, that's going to be negative work. So if force and the displacement vector are in the same direction, we're going to have positive work. But if they have opposite directions, it's going to be negative work because the force is acting in the opposite direction. Okay, so let's look at an example here. Calculate the work done when applying a force and look at my force vector. It's has an x component here, a y component, and a z component, and the distance of, and then 10, 0, 0. So my x, y, and z components. So looking at this example here, we're traveling a distance of 10 meters. So that's why it says 10 meters down here. And the force we apply is going to be 20 newtons in the x direction. So here it's moving along the x direction, as we can see this force vector. It's not going along the y or the z direction. And so using our equation for work, which is the dot product of force and the displacement vector, we're going to have in the x direction 20 newtons. That's going to move 10 meters along the x-axis. And then for our other components, the y component of the force is 0. The y component of the displacement is 0. We don't move vertically, so that's why it's 0. 0 newtons in the x direction, sorry, in the z direction, and 0 meters in the z direction as well for the displacement. And so we're going to see the work. If you just do that simple calculation of 20 times 10, you're going to get 200. And so remember that the units of work is in joules. Now that we saw that example, we're going to talk now about the types of energy. So the first one we're going to bring up is translational kinetic energy. So translational kinetic energy is a form of mechanical energy associated with a moving or rotating body. So you can think of something that's moving or it's rotating around. And so it's the movement. So when you think of kinetic energy, think of moving. And so translational kinetic energy, how do we calculate it? So here, translational kinetic energy is represented with a capital T. And since it's energy, it's in units of joules, just like we saw. Work is energy, work's in unit of joules, energy is in units of joules. Translational kinetic energy is a form of energy, so that's why it's in units of joules. So the translational kinetic energy is equal to 1/2 the mass times the velocity squared. And so if you look at this illustration, you're going to notice this ball has potential energy. It's at a height. And so right now, you can see the height of the ball, it's pretty high up. So it has a lot of potential energy. It's high off the ground. And you're going to notice once you let go of that ball, it's going to start moving and falling towards the ground due to gravity. And so that ball's going to pick up speed as it starts to fall here. So that potential energy is converted into kinetic energy because it's now moving and it's getting closer and closer to the ground. And so that ball's going to pick up speed as it's falling. And so our translational kinetic energy, we would be able to calculate how much kinetic energy that ball has if we knew its mass and the velocity. So looking at the example they gave us, we have 1,000-kilogram elephant walking at 1 meters per second. So what is the kinetic energy of the elephant? Well, knowing our translational kinetic energy, using the equation, we were given the mass as 1,000 kilograms. And the speed of the elephant is 1 meter per second. And so knowing our velocity and our mass, we're able to calculate the translational kinetic energy, which is 500 joules. Now that we know that, we're going to talk about rotational kinetic energy. So the first one we talked about was translational. And so we just saw translational was when a body was moving. And so either in the X direction, as you can see here, or a body can be moving in the Y direction. So we can have a ball falling down. So that would be in the Y direction. And so we looked at translational, moving along basically in one direction, but we're now going to look at rotational, which is an object rotating. And you can think about the Earth, it rotates about its axis. So here, rotational kinetic energy is a form of mechanical energy associated with a body moving with instantaneous angular velocity. And so angular velocity is represented by omega, and it's about an instantaneous center. And so here, your instantaneous center is given by capital I, lowercase I sub c. And so the rotational kinetic energy, remember when we had translational kinetic energy? Same symbol here, capital T, but remember for translational, it was 1/2 m and then v squared. But here it's 1/2 I of IC times omega squared. And so instead of v, it's omega, and instead of mass, it's going to be the mass moment of inertia about an instantaneous center of rotation. And so looking at this, we're going to solve specifically for the rotational kinetic energy, but you can see if we have a mass here and it's rotating, we have a rotation of this mass around its center point that I marked in red here. We have rotational kinetic energy. And so what we're going to notice is the rotational kinetic energies in units of joules, the mass moment of inertia about the instantaneous center rotation is given in kilograms times meters squared. And then our angular velocity is given in terms of radians per second. So it is equal to the velocity divided by specifically here our R, and our R represents our displacement vector. And so that's what we have here. And then for mass of length, it's the radius, my bad, not the displacement vector. And so for a mass of length capital L and a total mass of lowercase m, the mass moment of inertia is equal to ml squared. And so what we're going to see here, this is a mass of length L. And so what we're going to have is this equation. But if we have a uniform disk of radius r and a total mass of m, the mass moment of inertia is given by this equation here. And so the total kinetic energy is the summation of the rotational kinetic energy and the translational kinetic energy. So these two components make the entire kinetic energy. And so we're going to look specifically at an example, which is going to use a rotational kinetic energy. So this example talks about a 7 kilogram homogeneous disk of 5 centimeters radius. And so right here, if we're looking at this disk, it has a 5 centimeters radius, rotates on a massless axle AB. And so right here, it's talking about the axle. And so here from A to B, so this axle is what's indicated in orange here of length 0.5 meters. And so that axle is 0.5 meters long and rotates about a fixed point A. So at this point, it is fixed, so it's going to be rotating around A. So we can see this rotation around that point. The disk is constrained to roll on the horizontal floor. And so it's a horizontal floor, right? It's horizontal, it's not vertical, so it's horizontal. So we can see the disk right here is going to rotate about the floor and move in a circle and return to its location. So that's what we're going to notice. Knowing that omega is equal to 20 radians per second about the x-axis, so this is indicating that we have our rotational kinetic energy, we're given omega, and omega equals 2 radians per second about the y-axis. Determine the rotational kinetic energy. And so looking at this example, remember for rotational kinetic energy, it's given by the following formula. And so we're going to have this disk rotating. And so we're going to see the disk is going to rotate. And we're also going to have the rotation about this center point A. And so what we're going to have to do here is our disk. Remember the equation that we're going to have for our mass moment of inertia about an instantaneous center? Well, looking at the disk first, we have that component. So plugging in the mass of the disk, the mass of the disk was 7 kilograms, and then it had 5 centimeters radius here. And then for the next part of the equation, it's going to be rotating about this center point A, that length of this axle rotating. And so what we're going to see here is, remember that axle is 0.5 meters. And so we know specifically the mass they gave us in the problem in 0.5 meters, so it's the length of that axle. Remember, when it's just of length L, because the axle is just in length L, you use the ml squared for the instantaneous center, calculating that moment of inertia. And then using our omega, so the omega that we're plugging in here for our disk, what it's going to be is 20 radians per second, whereas our omega for our axle is going to be 2 radians per second. And so using those, we're going to get a total rotational kinetic energy of 5.25 joules. Okay, now that we saw that, we're going to look at basically, as I repeated before, the total kinetic energy is the summation of the translational, moving on a specific axis, and rotational, so moving about a center point, kinetic energies. So we can see if you have to find the total kinetic energy, you sum the two together. Now, we're going to look at an example where we're given a uniform disk with a mass of 7 kilograms. So this disk right here has a mass of 7 kilograms, and it has a diameter of 3 meters. And so we know this disk has a diameter of 3 meters. Rolls on without slipping on a flat horizontal surface as shown. So it's rolling along here. So we can see they show the rotational and it is moving with a velocity of 50 kilometers per I believe this per hour. And so what we're going to determine is it's moving along the x-axis at 50 kilometers per hour. So we know the mass of the disk, we know its diameter, and we know that has a rotational part where it's moving, and it has also a translational part because it's moving along the x-axis. It's not just rotating. And so turning the horizontal velocity basically into meters per second, so we're converting it from this kilometer per hour. Remember, there's 1,000 meters in a kilometer, and in 1 hour, there's 3,600 seconds. So getting it in terms of actual metric units and finding the angular velocity. Remember, angular velocity is the velocity divided by the radius. And so the radius is the diameter divided by 2. So 3 meters divided by 2 gives us our radius. And so we'll be able to calculate our angular velocity. Now, with our angular velocity now known, we can find our total kinetic energy. And so right now our translational kinetic energy is going to be 1/2 times the mass of the disk, which is 7 kilograms, times, and this is the horizontal velocity squared, because that's the translational part. It's moving along the horizontal axis. Now, we need to find the rotational part. And so the rotational part, remember, we're working with a disk. So our mass moment of inertia around an instantaneous center is given by 1/2 mr squared. Now, plugging in the mass of the disk is 7 kilograms. Our radius is given by the diameter divided by 2. And our omega in this problem, if you notice, we were able to calculate our angular velocity by taking our horizontal velocity and dividing it by the radius of the disk. And so plugging in that now for our angular velocity, we're able to get a total kinetic energy of 1,012.894 joules. Okay, now that we discussed that, we're going to look at a change in kinetic energy. So a change in kinetic energy is often represented by a change in the kinetic energy here. We see the delta symbol, which is the final kinetic energy. So you can represent that by T2 minus the initial kinetic energy represented by T1. And so what we're going to see here is 1/2 mass times velocity squared minus 1/2 mass times velocity squared. V2 represents the final velocity, where V1 represents the initial velocity. So that's what we represent here. And so for the gravitational potential energy, now talking about potential energy, it's represented by the symbol U. It's a type of mechanical energy associated with mass by its relative position in a gravitational field. And so what we're going to see here is the gravitational potential energy is given by the mass times the local acceleration of gravity times the height. And so right here, we're going to notice that the biker, look at the example, has kinetic energy while he's biking up the hill. And then at the top of the hill, he's going to stop up here. So he's at the top of his potential energy. He's stopped right here, and he has a lot of potential. Because look at the difference in the height. He's at a high potential because he's at a higher height than his surroundings. So he's at a higher potential than what the surrounding height is at. And so he has more ability to do work because if he moves to the left or right, he's going to start moving. And so what's going to happen is he's going to start moving, and that potential energy is going to be converted to kinetic energy because he's going to be in action. And so what's going to happen is we notice he's building up potential energy as he gets higher and higher here. So this is the buildup of potential energy. Then he reaches his max potential energy because he's at the highest potential. And then he's going to start losing that potential energy in increasing in his kinetic energy as he falls down the hill. And so what we're going to see here is the energy, what you notice, it wasn't destroyed. It was just converted from kinetic energy to potential energy and then back to kinetic energy. And so take note of that. Now we're going to look at spring force. So a spring is an energy storage device because the amount of energy it can store is equivalent to the work required to compress the spring, because it takes work. If you squeeze the spring together, that takes work because it naturally wants to balance out. So it will like start to balance out after you compress it. It will start to like go back and forth until it reaches a state of equilibrium. So a spring can store energy if you compress it. So looking at the spring force, also known as Hooke's law, the force in a spring, which is given in newtons, is equal to the spring constant. So the spring constant here, we're going to see is given by K. So K is going to be the spring constant, and it's given in units of newtons per meter, and the displacement X, which is given in units of meters. And so what we're going to see in the diagram down below is that our spring constant here, you're going to notice a minus sign here because notice that it's going downwards. That spring down in the y direction. So that's what we have here. The minus sign is to account for the displacement, the negative displacement, because it's going downwards. So it's going to take twice as much force to stretch a spring twice as far because you have to go double the distance. So if you have to go double the distance, it's going to increase the force by twice the amount. So just looking at that proportion. So let's look at an example. A spring has a constant of 50 newtons per meter. So right off the bat, this is your K value here in your equation, 50 newtons per meter. The spring is hung vertically. So here, if we have our spring, it's hung vertically. And the mass is attached to the end. So I have a mass here. So I'm going to represent that with our box. The spring end displaces 0.03 meters from its equilibrium position. And so it's going to be 0.03 meters different. And then the same mass is removed from the first spring and attached to the end of a second spring. And the displacement is 0.025 meters. Calculate the spring constant of the second spring. Okay, so it's going to be taken off that spring and it's going to be attached to the second spring. And so what we're going to see here, it's the same mass. It was just taken from spring 1 and it was moved over to spring 2. And so here we have our spring 1. And over here, we're going to have our spring 2. Okay, so what we have here is this one is displaced on spring 1. The amount of displacement from its original equilibrium value, the spring, is going to be 0.03 meters. So we know. Where the amount of displacement here on our second spring is going to be 0.025 meters. So it's going to be less displacement here, just so we know on the second spring compared to the first spring. And so what's going to happen here is using our equation. So we need to calculate the spring constant of the second spring. And so since we're going to be looking at these two springs and they have the same amount of force. Why is that? Because there's only one force acting on both these systems, and that's the gravitational force. So remember, gravity is going to be pushing down, so the force of gravity. So the force on spring 1, the force of gravity is going to equal the force on spring 2 because it's the same force applied to both systems. So that's why we can write the force on spring 1 is equal to the force on spring 2. Now, substituting in for forces, using the force in a spring, just substituting in K and X, and now solving for the spring constant for the second spring, so just rewriting the equation by dividing by X sub 2 on both sides. Now we're going to plug in the spring constant of the first spring multiplied by the displacement of the first spring, all divided by the displacement of the second spring. And that's going to give us the spring constant of our second spring. And so that's how we were able to solve the problem. Now looking at elastic potential energy, remember, this is a type of potential energy, so it's written in terms of U. It's a type of mechanical energy associated with a spring's elasticity. So this would be how elastic is your spring. And so how much can it be like pulled out or compressed? So stretched or compressed, the elasticity of your spring. And so it's given by 1/2 times the spring constant times the displacement squared. And so what we're going to see is that how much elastic potential energy it has. So when it's compressed or stretched, a spring's going to have elastic potential energy. And so the change in potential energy is the difference between the initial and final potential energy. And so that can also be written as delta U, which is equal to the final value of potential energy minus the initial value of potential energy. And so remember substituting in for our potential energy here. What we're going to notice is that we're going to have specifically 1/2 our spring constant times the displacement squared minus 1/2 our spring constant times the displacement squared. And this would be the final displacement minus the initial displacement. And so just notice that it's just the change in the potential energy. So you subtract, basically you have your final value minus your initial value for your potential energy. Now, we're going to look at the energy conservation principle, which states that energy can neither be created nor destroyed. And so what we're going to notice here is that the summation of all the energies is constant. And so energy can be transferred into a different form, but you can't destroy or create energy. Within that system, that energy has to remain there. It can't just all of a sudden disappear. And so work must be performed to transform the energy. And so if we're changing from one form of energy to another, work must be actually created, or work must be executed or performed in order to change the type of energy, because energy can neither be created nor destroyed. Okay, so right here, you're going to see that the final kinetic energy and the final potential energy is going to be equal to the initial kinetic energy and initial potential energy. This is just saying that the final energy is going to equal the initial energy, because energy can neither be created nor destroyed. And so right here, your final energy is the final kinetic energy plus the final potential energy is equivalent to the initial kinetic energy plus the initial potential energy. So for conservative systems have no energy dissipation or gain. The total energy of one mass is equal to the sum of its kinetic and potential energies. And so within this example here, you're going to notice that when you provide electricity to a light bulb, that energy is converted to light. And so that's why we see the light, is you're feeding it electricity. And it converts that electricity into light and also heat, because it gives off heat, that bulb. So we're going to notice that energy is being converted into a different form. So that electricity that you're feeding in is converted into heat and light energy. Okay, now we're going to look at an example using the law of conservation of energy. So here, a projectile with a mass of 10 kilograms is fired directly upward from ground level with an initial velocity of 1,000 meters per second. Neglecting the effects of air resistance, what will be the speed of the projectile when it's 1 meter above the ground? So using the law of conservation of energy, what we're going to notice is basically our projectile we have. So I'm just going to draw our projectile as this mass. It's going to go and shoot upward from ground level with an initial velocity. So our initial velocity here is going to be 1,000 meters per second. Neglecting the effects of air resistance, what will be the speed of the projectile when it is 1 meter above the ground? So when it's 1 meter here above the ground, what is its speed going to be? And so here, if we have to calculate the initial kinetic energy, which is 1/2 the mass times the initial velocity squared, so we're going to get 5 megajoules. And then calculating our initial potential energy, right here we have our mass times the gravity, the local acceleration of gravity. And notice though, it does not have any potential energy because it's at 0 meters. It's at the ground initially. So it's originally at 0 meters. So it's not at any height. It doesn't have any potential compared to its surroundings. So it's at 0 right now. And so the final, it's going to be at 1 meter. So it's not going to have potential. It's going to be at a specific height. It's going to have energy because then it can fall back down. And so that's why here the final potential energy we are able to calculate as 98.1 joules. So using our law of conservation of energy here, we're going to notice if you write it out and solve it in terms of our final kinetic energy, substituting what we know, we're going to be able to find that the final kinetic energy is approximately given by 4,999,901.9 joules. And so if we want to solve for the velocity, remember, kinetic energy can be written in the form 1/2 the mass times the velocity squared. And so writing now this equation in terms of velocity and substituting in our known variables, we're able to find that the velocity is approximately 1,000 meters per second. Okay, now we're going to talk about momentum. Momentum is a characteristic of an object, and it refers to an object's mass and velocity. So it takes the product of the two. And so momentum, what we're going to see is dependent upon the size and the speed. And so a larger momentum could be like a truck. A truck has a very large mass. And so this truck right here, we're going to see has a larger momentum because when it's traveling at a fast speed, it's going to be harder for it to stop. But we're going to see for a small car, it's going to have a lot smaller momentum because it is traveling at a slower speed and it is greatly reduced in size. So we're going to see here that it has a smaller momentum because it has a smaller mass and a smaller velocity. Okay, now we're going to talk about the impulse momentum. An impulse is a change in momentum. So remember the delta here just represents a change in the momentum, the final minus the initial. So, or a change in velocity with constant mass. So remember, momentum can be written as the mass times the velocity. But here, if we're talking about the change in momentum, the mass remains the same. The mass doesn't change, but the velocity does. And so that's why we wrote the delta next to the velocity if we're talking about a change in momentum. Or it can be written in as a change in force over time. And so our force and then multiplied by, and then it's a change in time. So that's why the delta, the force is the same, it remains constant, but the time changes. And so from the impulse momentum principle here, we're able to see that an impulse is a change in momentum, which is equivalent to writing the mass times the change in the velocity, which is equivalent to the force times the change in time. So as we can see here, the impulse is calculated as the change in time, which we see from T1 to T2, and then it's going to be multiplied by the force. And so a simple proof is, remember, from Newton's second law, force is equal to the mass times the acceleration. And the derivative of velocity here will give you acceleration. So we're substituting in for acceleration, the derivative of velocity. Now, rewriting the equation, so we multiply both sides by dt, we're going to get force times dt is equal to mdv. Now we're going to see that substituting in for dt, the change in time, with delta t, and substituting for the change in velocity with delta v. And so that's how we're able to rewrite our momentum principle in terms of force times the change in time. Because we know momentum is defined as the mass times the velocity. And so that's why we're able to substitute in for it, the force times the change in time. Okay, now we're going to look at an example where a 60,000 kilogram rail car moves at 1 kilometer per hour. Is coupled to a second stationary rail car. If the velocity of the two cars after coupling is 0.2 meters per second, and the coupling is completed in 0.5 seconds, what is the impulsive force on the rail car? Okay, so originally we're going to have our first rail car. And so calculating our mass we know is 60,000 and our velocity is given by 0.278 meters per second. And we're going to see the second one, what we're going to notice is the velocity after the first and the second car are coupled together. So originally just we have our first car moving and the second one stationary. And so what we're going to see is we're going to have our first car moving and then our second one stationary. And so once that first car couples, so it is coupled against, so then it is touching the second one. Then they're both going to be moving at a specific velocity. And so the velocity, once they are coupled together, is 0.2 meters per second. So now this velocity is 0.2 meters per second that they're moving with. Initially, the second mass here had 0 meters per second. It wasn't moving, but the first car was moving with a velocity of 0.278 meters per second. So this arrow right here was 0.278 meters per second. Okay. And so it initially started at time 0 and it went up to 0.5 seconds. That's what the couplings completed in 0.5 seconds. And so now we're going to see the impulse momentum principle that solving this equation in terms of the force, you're going to be able to put it now in terms of the mass times the change in velocity all over the change in time. And so substituting in our variables, here what we're going to see is that our mass of the rail car was 60,000, so it didn't change the mass. And the final velocity is 0.2. The initial velocity is 0.278. And then the final time was 0.5 seconds, and initial time was 0 seconds. So we were able to get, our force was negative 9,360. And so remember that the problem was asking about the impulsive force on the rail car. Doesn't it make sense? Because now it's the car was moving, but then it coupled against the other one. And so when it coupled against the other one, it sort of slowed it down. So like it sort of pushed back because initially the second rail car doesn't want to move. It has to build up. So there's sort of a pushback force. And so when it hit and collided with that second rail car, and so it makes sense that we have a negative value here. Okay, now looking at power, power is the amount of work per unit time. And so what we're going to see is that power is the dot product of force and velocity, or it can also be represented as a product of the magnitudes. And so power here is the amount of work per unit time. And so that's what we see here, the amount of work per unit time. And it can also be calculated as the dot product of the force and the velocity. Or if you just want to do the magnitude, so the magnitude of the force times the magnitude of the velocity to give you your power, because those would both be scalars to give you a scalar at the output. Okay, so looking at an example, it asks us calculate the power from a truck that has a force of 100 newtons and a velocity of 20 meters per second. And so using our equation, if we know the force of the truck, so that'd be how much force it has that it's pushing with, and then the velocity is 20 meters per second, we're going to see that the power is 2,000 watts. So we were able to, if you take the magnitude instead, remember we said you can do the dot product if it's a vector quantity, or if you take the magnitude, then both are scalars, so the output would just be scalar, and the power is measured as a scalar quantity. And so it'd just be the force, the magnitude of the force times the magnitude of the velocity. And so the scalar quantities would be 100 newtons times 20 meters per second. So now that we're able to calculate all that, we were able to look at the energy, all the different types of energy, work, and also look at power. And so that was basically the entire chapter, was looking at how energy can neither be created nor destroyed. And so that law of conservation of energy is very important in terms of seeing how energy is converted into other forms, and how work basically represents it is equivalent in terms of units as energy. It's basically the ability for an object to perform work means that has energy. And so that's what we were able to see within this lecture. Thank you for watching.